Hi, my name is Tálita. I am a PhD student at PUC-Rio. My research is about the effect of interfacial rheology on drop coalescence in water in oil emulsion. My advisor is Professor Márcio Carvalho. Our work is motivated by the necessity to understand more about this mixture called by emulsion. Emulsions are a mixture of two immiscible liquids in the presence of an agent emulsified, commonly known as surfactant. Here on the left, we have only water and oil, and on the right side, we added one surfactant. If you try to mix only the water and the oil phase, after a moment, they will separate again. But in the presence of surfactant, they can go together for long periods of time. Emulsions are more common than we imagine. Some examples are our foods, cosmetics, pharmaceutical products, inks, and even in the oil industry. With several applications, a great number of studies have been carried out to better understand the formation, its properties, and also an important characteristic, its stability. In some cases, they are desired, but in the other, they can be a problem, as occur in the oil industry, where the emulsions are formed during all the production process and need to be separated on the end. The separation process is called by coalescence, based in a merge of two pieces of a same phase or miscible phase. When we have the approximation of two drops, due to the pressure, the liquid is squeezed out into the bulk, resulting in a convective flux of surfactant in the sublayer. Therefore, we can observe that the surfactant concentration is increasing in this direction, creating a weak zone in the middle of these drops. This is a complex problem that involves a multiple flux occurring at the same time. In this video, we can see this process occurring. We have a lot of small droplets coming together and becoming bigger and bigger until the total separation of the phase. So the objective of this work is to understand more about this separation process through the coalescence of two water droplets by the influence of different surfactant concentration. To perform these experiments, we used a milky water and an oil phase composed by a mixture of Primol and Span 80 as the surfactant. The coalescence events will be studied into a cuvette, and in this figure, we want to highlight the dispositive on the bottom. This is a simple piece in which there are some holes where we can centralize better one of the drops, and that allowed us to run more than one experiment before clean all the devices without compromising the results. The interfacial rheological properties were obtained using the dependent drop method, in which we measured the interfacial tension and the elastic and the viscous moduli. Here we have the coalescence experiment setup, composed by a syringe pump used to form the drops, a pressure transducer used to measure with accuracy the time, high-speed camera, computer, light system, lift, and a cuvette. This is a photograph of our setup. Now, I'm going to show you two videos presenting the process analyzed. In the first one, we have the drops formation. We started with the injection of the first drop volume, as we can see. Right after the formation, we moved down the cuvette using the lift. And after, we started the injection of the second drop volume. Observe that because of this device that I talked, the centering of the drop is more precise, and we can prevent the lateral sliding of the droplet on the bottom. We wait a certain time. After that, we move the drops against each other, and when occur the contact, we wait to drainage of the oil film remain between them, and finally the coalescence occurs. Now I will start the results with the oscillatory tests that were performed with these conditions here. We evaluated 4 different surfactant concentrations. The experiment without surfactant showed the interfacial tension value about 14.5 millinewton per meter, but in the presence of surfactant, we observe a considerable reduction of this property, measuring between 1.5 and 2 millinewton per meter. Comparing all the concentrations, there is not a significant difference in the interfacial tension values that should explain the behaviors observed on the coalescence experiments that we are going to see. But the interfacial, elastic, and viscous moduli could be responsible for these behaviors. So, if we analyze these moduli, in general, the viscous modulus start higher than the elastic modulus, and after some time, they inverted each other. Only for the smallest concentration, we cannot identify better this inversion point, because in the beginning, the moduli have values very similar. However, as we increase the surfactant concentration, this inversion occurs at different moments and should be related to the desorption time of the surfactant on the interface. With 1% in weight, after the inversion point, the moduli started to rise in opposite direction. For the other 2 highest surfactant concentrations, this point occurred earlier, and after that, the elastic modulus rapidly grew, whereas the viscous modulus step decreased with time, reaching 0. These results showed that we obtained a strongly elastic interface with this surfactant. We performed the coalescence experiments up to 1 hour of drops aging time, as I will show later. Consequently, our oscillatory tests had the same duration, but as we could see on these tests, the highest surfactant concentrations presented different behaviors from the smallest surfactant concentrations. So we decided to increase the experiment time for the smallest concentrations. And with more time, the surfactant seems had enough time to adsorb at the interface and present similar behavior to the highest surfactant concentrations. We observed that the second decrease of interfacial tension seems to related with the moment that the viscous modulus tends to 0 and the elastic modulus reaches a maximum value. Also, the maximum elastic modulus is different for each surfactant concentration and increases as the concentration increases too. Here, we evaluated the influence of the aging time before the oscillations on the interfacial rheological properties, only for the highest surfactant concentration. We can see that the properties behavior does not change with the drop aging before the beginning. If we move the data to begin at the same moment of the experiment without interface aging before the oscillations, the shape of the curves presents similar behavior. Before to present the coalescence results, I need to define the times that we are measuring at this experiment. We are going to measure the time before the contact of the drops as the first time, called by the aging time, and the time between the contact and the coalescence process as the second time, called by drainage time. So we are going to have a relation between them. Here we have this relation for the surfactant concentrations evaluated. The time referring to the experiment without surfactant is not represented in the graph since the coalescence occurs almost instantly, taking only a few milliseconds, which is much shorter than the others observed. The results are an average of more than 6 experiments with the respective values of standard deviation. When the coalescence occurred, the drainage time showed no dependence with aging time, neither with surfactant concentration. In some cases, the drops did not coalesce. These results are plotted in the graph with time equal 1 hour only to representation. In this case, we observed a formation of a solid-like interface that can be responsible to prevent this process. With concentration of 1.5%, this phenomenon was evidenced only after 1 hour of drops aging, whereas for concentration of 2%, this behavior began with 10 minutes. In this concentration, the time interval between 10 and 30 minutes was more investigated, showing results with a random pattern. The same aging time presented both coalescence and no coalescence of the drops. I would like to emphasize that to construct this plot, we performed experiments with 1 hour of drops aging time. But as we saw with the rheological properties, maybe this scheme took more time to form with the smallest surfactant concentrations. So we decided to increase the aging time for the smallest surfactant concentrations. For 1% of our surfactant, we waited for 2 hours, and in this case, as we expected, the coalescence did not happen, as we can see in these images. It's important to remember that as we performed our experiments with 1 hour of duration, now we have a window for this concentration between 1 and 2 hours to find the exact moment that this scheme is strong enough to avoid the coalescence. The same thing was done to 0.5% of our surfactant, but now with 4 hours of aging time. And again, the coalescence did not happen. So for this surfactant concentration, the window that should be tested is between 1 and 4 hours. After 2 hours waiting the coalescence process, we increased the drop volume and we only observed the break of this interface. Here we have some videos. The first one represents the case that this scheme is not formed yet and the coalescence has this pattern. The second shows the coalescence occurring for concentration of 1% and 1 hour of aging time. And we noticed that even the coalescence occurring, the rupture was no longer symmetrical, indicating that there is a higher resistance to coalescence between the drops due to the presence of the skin. But this skin is not strong enough to prevent the event. However, in the third video, we can see that this skin is more structured because even try to deform the drops and after separate them, the coalescence did not happen. Finally, in this video, we increase the drop volume and we can see the rupture of this structure. As our final remarks, we evaluated different surfactant concentration of SPAN 80 and also the dependence of film drainage time with the aging time of interface for each concentration. When the coalescence occurred, the drainage time seems not to be related with the aging time, neither with the surfactant concentrations. And when the coalescence did not occur, we observed a formation of a solid-like structure on the drop surface, representing the strong activity of surfactant migration from the bulk region to the interface, creating an elastic film at the interface. The interfacial tension did not present significant difference between the concentrations studied. However, the elastic and viscous moduli showed that the surface viscoelasticity plays an important role in coalescence process. As our future steps, we are going to investigate how to promote the destabilization of these strong interfaces through weakening the interface elastic modulus chemically or mechanically, for example, increase the drop area. I would like to thank to all funding agencies and for your attention.